College for Girls, Amritsar. Hello students, myself Jaibir Singh, Senior Lecturer, Government Polytechnic College for Girls, Amritsar. In today's lecture, we will study the working of very important digital circuits, flip-flops. So, in this session of EduSat lecture, our session objectives are to describe the operation of a basic RS flip-flop and explain the purpose of additional input on the gated input, that is clocked RS flip-flop. Explain the truth table for edge triggered RS flip-flop and edge triggered D flip-flop. In this session, we will also discuss some of the timing problems related to the flip-flops. Now, what is a flip-flop? In a combinational digital circuit, the output of the circuit is dependent upon the current input, but the circuit which are having memories, they are called as the sequential circuits. So, flip-flop is the main part of the sequential circuits in digital electronics. So, a flip-flop is a bistable electronic circuit that has two stable output states, that is, its output is either 0 or plus 5 volts, or we can say its output can be either 1 or 0 or low or high. The flip-flop also has memory. What do we mean by this point? The memory means since its output will remain in its last state until something is done to change it. So, even if the input is replaced or disconnected, the output of the flip-flop will stay in the last state until and unless we do or we apply some signal to change its output state. The flip-flop can be regarded as a memory device. For instance, when the flip-flop has its output set to 0 volt, it can be regarded as storing a logic 0, and when its output is set at plus 5 volts, it is regarded as storing a logic 1. So, basically flip-flop is a bistable digital switch which can be set or reset, or which can be on or off by applying a suitable input signal at its input. The flip-flop is often called latch, since it will hold or latch in one of either stable states. So, in digital electronics, there are numerous applications of the flip-flops. So, mostly I have mentioned some of them in this slide. So, flip-flop are used in the construction of shift registers, that is in which we can store binary data, counter circuits in which we can do the counting operations, timers, frequency divider, and etc. Now, first of all, we will discuss the construction of a basic RS flip-flop using NOR gates. I presume that all of my students listening to the lecture are familiar with the various gates in the digital electronics. Again, I am repeating, we are using here a NOR gate. NOR gate is a digital gate in which OR gate is followed by a NOT gate. So, in combine we will call it as a NOR gate. Now, in the NOR gate, the output of the NOR gate is high when both the input are low, otherwise the output is always high. So, here we will see we have two inputs. One input is named as R input or reset input. The other input is named as S or set input. We are using these two NOR gates, and we have two outputs, output Q and Q bar, which is the complement of the Q output. The condition of a flip flop is that its two outputs are always complement of each other. This is the basic definition which must not be violated in any case. So, here you see the one upper output, that is the Q output, is feedback to the lower NOR gate, and the complemented output is feedback to the upper NOR gate. So, this is the circuit diagram of a basic RS flip flop using NOR gate. To explain how it is working, we will study the truth table of this gate now. What is a truth table? I must tell you, truth table is the tabular representation of working of a circuit. And what is there in the truth table? Truth table includes all values of possible combinations of inputs and corresponding outputs. So, a truth table explains the working of a given circuit. We have again the same circuit which was there in the previous slide, having two NOR gates. One input is R and that NOR gate output is Q, and we have a S input, which is, we can say, set input, and that NOR gate output is Q bar. So, by giving the various combination of possible inputs at the inputs of the circuit, we will see how this works. So, we have to presume for first input combination, we have to presume any one of the output state, or we have to assume either the flip flop is previously set or reset, and both outputs are complements of each other. So, I will assume previously this flip flop is in the set condition, that is, its Q output is 1 and Q bar output is 0, because these two outputs are complement of each other, and apply a 0 logic at set input and a 0 logic at reset input. Now, previously the flip flop is in the set condition, that is Q is 1. When this one input is given here and the other input is also 0, both inputs to the OR gate are 0 and the output of OR gate is 0, and there is a NOT gate after the OR gate. So, Q bar will be 1, which is the previous state, and when this output is 1 and this input is 0, both inputs are 0 and this output again is equal to 1. So, it will stay in the last state, in the state where it is lying previous to the by applying these two logic levels at 0. Now, we assume that this is in the reset state. In the reset state means the Q output is 0 and Q bar output is 1. In the reset state, now both inputs are 0 and output is 1, and here both inputs are 0. So, here also output we will be having the last state, that is the 0 value will be coming here. So, when we apply S and R inputs, both inputs to zeros to this flip flop, there will be no change in the output, or output stays in its last value. Now, we will see what happens to this outputs of this circuit when we apply a 0 input at S and a 1 input at reset. When we will apply a 0 input at the set input of this flip flop and one input at the one input at the reset input of the flip flop, this will shift this flip flop into a reset state. We say this flip flop is in the reset state when Q bar is equal to 1 and Q is equal to 0. If Q is equal to 0, we call this flip flop is in the reset state. So, next input combination in this truth table, we apply S input as 1 and R input as 0. This input will cause this flip flop to move into a set state, that is Q output will be 1 irrespective of the last state, because if it is already set, then Q is equal to 1, both inputs 1 at the input of this NOR gate will shift this as 0 and both inputs 0 at this inputs of this NOR gate will shift this output as 1. So, it will be set irrespective of the last state. If it is previously in the reset state, that is Q bar is equal to 1. So, this will again shift this flip flop into the set state. So, by applying a S input 1, it will go into the set state, that is Q is equal to 1. Now, very important entry in this truth table is when we turn both inputs as 1. This state is called as the invalid or forbidden state, which we say which must not never be applied to this flip flop. ਇਹ ਕੰਡੀਸ਼ਨ ਅਸੀਂ ਕਦੀ ਵੀ ਇਸ RS flip flop ਦੇ inputs ਦੇ ਉੱਤੇ ਅਪਲਾਈ ਨਹੀਂ ਕਰਨੀ ਹੈ, because when we apply both set and reset inputs of the flip flop at logic 1, any one input to the NOR gate will cause the output will be 0, and this input will also cause the output to be 0. So, both outputs Q and Q bar will go into the 0 state, which against our basic definition of the NOR gate, that RS flip flop, that is the outputs are complement of each other. But if we apply this S and R input, both inputs as 1, the output will not be complement of each other and they will be 0, and this is not recommended, and this is called as the forbidden or invalid state, which must not be never applied to the inputs of the flip flops. Now, working of RS flip flop, in this slide we are again repeating what we have discussed previously. Flip flop has two inputs defined as R and S. The flip flop has two outputs Q and its complement Q bar. The first input condition in the truth table is R is equal to 0 and S is equal to 0. Since a 0 at the input of a NOR gate has no effect on its output, the flip flop simply remains in its present state, that is Q remains unchanged. The second input condition in the truth table is R is equal to 0 and S is equal to 1. This condition forces the NOR gate a R low, and now the NOR gate output must be high. Thus, 1 at the S input is said to be set the flip flop and it switches to the stable state where Q is equal to 1 and Q bar is equal to 0. In the third entry of the truth table, the third input condition R is equal to 1 and S is equal to 0. This condition forces the output of NOR gate as a low, since both inputs to NOR gate B are now low. The output must be high. Thus, 1 at the R input set to be reset the flip flop and it switches to the stable state where Q is equal to 0 and Q bar is equal to 1. And this is, in this case, the flip flop is set to be off. The last input condition in the truth table is R is equal to 1 and S is equal to 1. This is a forbidden state as it forces the output of both gates to the low state. This violates the basic definition of the flip-flop that requires Q to be complement of Q bar. So, this input condition is never imposed. The resulting state of Q is not predictable. That is why this entry in RS flip-flop is always forbidden and this must not be applied. Now, we can also construct a RS flip-flop using the NAND gates. In this case, you see we are using again two NAND gates and the output of the flip-flop are Q and Q bar, and it is fed back to the gates. Outputs are feedback to the input side by this path, and here an additional, when we are using a circuit using NAND gates, we have additional gates. Here we are using the NAND gate, two NAND gates, and here I have also shown a enable input or clock input is added in the circuit. So, this the circuit diagram of a RS flip-flop using NAND gate. This slide shows the logic symbol irrespective of the gates being used to construct the RS flip-flop, whether it is a NOR gate RS flip-flop or a NAND gate RS flip-flop. We have this logic symbol in which we have two inputs S and R, two outputs Q and Q bar, which are complement to the each other. Any high input as the at the S input of the flip-flop will take this this flip-flop into a set state, and any high input on the R input of the flip-flop will carry this flip-flop into the reset state. Reset state means the Q bar output is 1 and Q output is 0. So, here we have shown the truth table for the NAND gate flip-flop, both inputs 0, the flip-flop stays in the last value. One input is R input is 0 and S input is 1, it will take the flip-flop into the set state. If R is equal to 1 and S input is equal to logic 0, then it will be reset, and when both inputs are 1, this state is a forbidden state which must be avoided at all times. Now, in the digital circuits, sometimes additional input is added which is known as the enable input. When we add this additional input before giving the R and S inputs to the latch or flip-flop, this type of flip-flop is known as the gated RS flip-flop. Here R and S input is given to the gate through a AND gate, and additional input enable is also added, and objective of this enable input is that when this enable input is high or at logic 1, then only this flip-flop works normally, that is any input on the set or reset inputs will cause this flip-flop to turn on or turn off or make its outputs 0 or 1. But if this enable input is in the low state, or we can say the flip-flop is not enabled, in that case the inputs on the set or reset will have no effect on the working of this flip-flop, or they will have no effect on the output of this circuit, and it will stay in the last state even if this set and reset are changing to get an change in the output of the flip-flop. So, this enable signal, it must be there if we want to have effect of this set and reset inputs to the output of the flip-flop. So, in this slide we have shown the IEEE symbol of a enabled flip flop in which we have S input, R input, Q input output and Q bar output, and one additional input is added to the circuit, that is the enable input. And this enable input, how it is connected is given in this slide. In this enable input is given to the flip flop through two AND gates, and the one input to the AND gate is the enable. So, this set and reset will have their valid effect only when this enable input is high. So, here we have a truth table of RS flip flop with a enabled input. In this truth table, you see when the enable input is 1, then when both inputs are S and R are 0, there is no change in the output of the flip flop, that is it is in the last state. When enable input is 1, S input is 1 and R input is 0, this will take this flip flop into the set state. When enable input is 1, S input is 0 and R input is 1, this will cause this flip flop to be in the reset state. And when enable input is 1 and both S and R inputs are 1 1, this, as I mentioned earlier also, this is a illegal state. This must be not be to be applied to the flip flop, as this will cause the outputs not to be complement of each other, and this against the definition of our flip flop, that it has two outputs and outputs are complement of each other. And the last entry in this truth table is that when the enable input is 0. In this case, we have cross entries in the S and R input, that is it can be 0, it can be 1, but they have no effect on the output of the flip flop, that is Q1 output is Q1, that is no change, it stays in its last value. Now, we will discuss what is the D flip flops. Now, RS flip flop has two data inputs. To store a high bit, you need a high at the S input, and to store a low bit, you need a high at R input, that is the reset input. Now, generation of two signals to drive a flip flop is a disadvantage in many applications, because in digital electronics like shift registers, we are using only one input, or as a flip flop can store only one bit. So, most of the applications we are using one bit only, one input only. So, furthermore, forbidden condition of both R and S high may occur inadvertently. So, this led to the D flip flop, a circuit that needs only a single data inputs. This D flip flop is widely used in the shift registers application of digital electronics. So, in this diagram, we are showing the circuit diagram of D flip flop. Now, in this case, the S input is replaced by input D, and the R input is given by connecting a NOT gate with the S input, and we have added a C or clock signal here. In this, we have this clock signal and two enabled gate for enable the inputs to the input of the flip flop. We have two NOR gates and two outputs here, Q and Q bar, and which are being fed to the input. Outputs are fed back to the inputs of these two NOR gates. So, this is the circuit diagram of a D flip flop, in which we have only one input called as D. Basically, we have converted a RS flip flop into a D flip flop by connecting S input as D and by connecting R input as complement of the S input. So, the logic symbol of a D flip flop is, we have only one input D, we have a clock signal, we have two outputs Q and Q bar. Here in this slide, we have truth table of a D flip flop. We have enable signal 0. In that case, D is cross, that is it can be have a value 0, it can have a value 1, but this value will have no effect on the working of the flip flop and it will produce no change in the output. So, output stays in the last value. Now, other case, when enable input is 1, the D input is 0 will cause the flip flop to go into the reset state or off state. The Q output will be 0 and Q bar output will be 1. If enable input is 1 and D input is also 1, this will cause the flip flop to shift into the set state, that is output will be 1. Now, we discuss now edge triggered RS flip flops. In digital circuits, we are using the clock signals, and in the clock the transitions are taking place either at the positive edge or at the negative edge of the clock pulse. So, if the flip flops are used in a synchronous system, all digital circuits are synchronous because they are doing operation with respect to the clock. In that case, care must be taken to ensure that all flip flop inputs change state in synchronous with the clock. Now, two types of triggering is used in digital system. A clock signal is a square wave of fixed frequency and duty cycle. So, now in the synchronous systems, we use two types of triggering. One is positive edge triggering, the other is negative edge triggering. In the clock, when the clock signal changes its state from a low to high, that edge is called as the positive edge, and when the clock signal changes its states from a logic 1 to logic 0, that edge is called as the negative edge. Now, depending upon the transitions or the circuit operation which are taking place either at positive edge or negative edge, we will call it as a positive edge triggering or negative edge triggering. So, next very important flip flop is JK flip flop. As in previously we have seen that the flip flops they have one forbidden state, their both inputs are 1, the output is not remains the complement of each other. So, RS flip flop and D flip flop finds their application mostly in the shift registers where we want to store the binary data. But in the counters application and the timer application, we need JK flip flop. JK ARS flip flop can be converted into a JK flip flop by giving their feedback. You can see here, this is a RS flip flop and there is one more feedback here. This Q output of the RS flip flop is fed back to the input of the gate, and one additional gate is connected and it is given to the input of this gate, and the Q bar output of the RS flip flop is fed back to an additional gate and connected here, and two additional inputs are mentioned here, J and K, and this is a clocked flip flop and we have a clock signal here. So, we will see how this circuit will work now. If we see the truth table of this JK flip flop, we will see that when both inputs are 0 and there is a clock signal, the output stays in its last state if Q is equal to 1 or if the flip flop is set, it remains set. If it is reset, it remains reset, and Q bar also remains the same as previously, and we can say there is no change in the output of the circuit. Output of the circuit, that is, it is in the last state. The same way as in the RS flip flop, if J input is 0 and K input is 1, Then a clock signal is there. This arrow shows us a positive clock signal. In that case, we have Q output as 0 and Q bar output as 1. That is, the flip flop goes into a reset state. A low input at J input and a high input at K input will cause this flip flop to go into a reset state. And if we apply a high input at J and a low input at K, and there is a arrival of a clock pulse, it will cause this flip flop to shift into a set state. Set state means the Q output is 1 and Q bar output is 0, or we can say the flip flop is in the on condition. Now, beauty of the circuit is lies in the last entry of the truth table. If you remember, if we discuss when we discuss the RS flip flop using NOR gate and NAND gates, this entry when both inputs are high, this was forbidden, because in that case the output does not